All right, so here's a quick recap on ray diagrams and optics. So the first thing we need to know or need to identify is what we're looking at here. And looking at this diagram, I have a few things. I've got a lens. I've got this horizontal line that always runs perpendicular to the lens, and this is the optical axis. And I've got 2 points. I've got a point here and a point here. These are my focal points. And this arrow here is my object. Okay, so the first rule of drawing ray diagrams is to identify your object, and your first ray passes parallel to the optical axis where it enters the center of the lens. Now at this point, light is entering a denser medium and it's slowing down, and it's going to bend or refract in a straight line through the focal point on the opposite side of the lens and continue passing through. Our second ray kind of does the opposite, in that it passes through the focal point on the near side, on the side closest to the object, in a straight line into the center of the lens. Again, it's entering a more dense medium. It's going to bend or refract parallel to that optical axis. And our third ray is going to travel in a straight line from the top of the object straight through the direct center of this lens, where the lens and the optical axis intersect, and continue passing through unchanged. So ideally, all three of these rays should be drawn simultaneously. So here's our first ray, and it's going to enter there, parallel to the optical axis and into the center of the lens. Once it enters the center of the lens, it's going to refract through the focal point on the opposite side. My second ray is going to travel through the focal point on the near side and into the center of the lens, where it also refracts and bends parallel to the optical axis, just like so. Now, it's at this point where the three lines intersect. Now, I don't necessarily need all three lines to understand what's going to happen here, but the three lines can certainly help. And it's at this point where all three of these rays intersect that I have an image that is going to be formed. And I'll try my best to draw my new image. So the image should look exactly like the object. Now, the size might change, its orientation might change, and its position along the axis may change, but it's still going to be an arrow. And I notice that my object is upright, my image is inverted. And I'm looking at the size of this arrow compared to the size of this arrow, and it appears to be about the same size. So this object is same size, the image same size. It's inverted, and all inverted images are real images. So let's look at some examples. In my first diagram, I see I've got an object, an arrow here. I've got my lens, I've got my optical axis, and my two focal points. Okay? My first ray travels parallel to the optical axis and into the center of the lens. Once it enters the center of the lens, it's going to bend or refract through the focal point on the opposite side, just like so. My second ray is going to kind of do the opposite of that, and it's going to travel through the focal point on the near side and into the lens, where it's also going to refract and travel parallel to the optical axis. Now I can already see where these 2 points intersect. I have an idea of where this image is going to appear, but I'm going to go ahead and draw my third line anyway. And that third line travels straight through the center of the lens, passes through unchanged. Now my line is a little off because I'm trying to freehand these, but you understand that all three of those images, or all three of those rays, are going to intersect here. And it's at this point that I'm going to get an object that appears here. Now if I'm comparing the image size to the object size, I would say that this image is clearly the same size. Compared to my object, it is upside down, so I'm going to refer to it as being inverted. And all inverted images are real images. Now, what this tells me in the diagram is that my focal length is 3 centimeters. So that means that from here to here, that measurement is 3 centimeters. It's also saying that the object distance, DO, is 6 centimeters. So that means that from my object to the center of the lens, I have 6 centimeters. So if I'm trying to find the image distance, I want to know how far the image is from the lens. So my image appeared here, my lens is here, the image distance is how far that image is from the lens. So if you look at it, your focal length is 3 centimeters. Your object is at 6 centimeters. So if we try to determine how far the object is in relation to the focal length, you'll see that the object is appearing 2 times further than the focal length. Because 2 times the focal length is 6. 2 times 3 is 6. So I can classify this diagram, this object's position, as 2F. And objects that appear at 2F will always be the same size, inverted, and real images. So if I wanted to use my lens maker equation, I can solve for DI. So that equation will look like the inverse of F is equal to the inverse of the object distance plus the inverse of the image distance. So if I want to get DI by itself, I'm going to move the positive DO to the opposite side. So the opposite of a positive DO is a negative DO. So I end up with the inverse of F minus the inverse of my object distance is equal to the inverse of my DI. So I'll plug in my F here, so it'll be the inverse of 3 plus the inverse of 6 will equal the inverse of my image distance. And then from there I can solve for DI. If I look down here at my next diagram, you'll notice that the object is now on the focal point itself. And when objects are on the focal point itself, they experience or will demonstrate certain qualities. So let's go ahead and draw our diagram here. First ray passes through the center of the lens parallel to the axis. Second ray, or I'm sorry, the continuation of that ray is going to refract through the focal point on the opposite side. The second ray ideally needs to go through the focal point, but it's on the focal point, so that ray is not going to pass through the lens. And my third ray will pass through the center of the lens and continue unchanged. Now what you should notice is that these two rays that are formed are parallel to each other, which means they will never intersect. And if they never intersect, there will never be an image. So anytime that your focal point and your object are in the same position, the rays that are formed will be parallel. which means that there will never be an image and everything else is irrelevant. So here my object is on the focal point, so we can label this as 1F. Anytime your object is on the focal point, there will never be an image. And the last diagram is showing me the position of the object between the focal point and the lens. And there are certain characteristics of an image that appears when an object is between the focal point and the lens. So we would classify this as 0.5F because it's halfway between the focal point and the lens. So my first ray is going to travel parallel to the axis and into the center of the lens, where it's going to refract and bend, passing through the far side focal point. My second ray normally goes through the focal point that's on the same side of the object. However, this one is not going to pass through the lens. My third ray is going to pass through the center of the focal point, center of the lens, and remain unchanged. Now, you probably notice that these lines over here to the right will never intersect. To the right. But that doesn't mean they're parallel. They will intersect. They're only going to intersect on the same side as the object. So what I'm going to do is I'm going to extend my lines back behind the lens on the same side as the object. And if I extend this one out this way, and then I extend this one out this way, you see that they do intersect. And it's at this position that my image is going to be formed. And you can see that this image is significantly larger. It is no longer inverted, it is upright, and all upright images are virtual. So if I wanted to calculate the image distance, I'm going to use the same equation as I did before. So what I'm looking at here is that according to what I have written here, my focal length is 3. So from here to here, I have 3 centimeters. My object distance is at 2 centimeters. So from here to here, my object distance is 2 centimeters. I want to figure out what my image distance is from here to here. So the inverse of f is equal to the inverse of dO plus the inverse of di. If I want to figure out the image distance, then I'm going to move my object distance to the opposite side to get di by itself. So the inverse of f minus the inverse of dO equals the inverse of di. And I can plug in f as 3, I can plug in 2 as object distance, and solve for my image distance. Now what you should determine is that the image distance in this equation will give you a negative, and it's always going to be negative for virtual images. So the image distance is always negative for virtual images. For real images, the image distance will always be positive. So it's a positive di for real images. And a negative di for virtual images.